All right, let's tackle one of the absolute classics of system design, the URL shortener. Now, I know what you might be thinking. This is just some simple coding exercise, but we're not going to treat it like that. Nope. We're going to treat this as a masterclass in system architecture. We're going to reason from the ground up, from first principles, to build something that can actually survive the pure chaos of the real internet. So right off the bat, let's just destroy the most common misconception. If you think a URL shortener is just a service that takes a long string and makes it a short one, you are missing the entire point. Seriously, that mental model will lead you down a path to building a system that breaks, and I mean breaks badly. So here is the correct mental model. Let's break this down, because every word here matters. Globally read-heavy, that just means you're going to have way more clicks on links than you have people creating them. Adversarially accessed, this is the big one. It means you have to assume that people will try to break your system. They will try to scrape it. They will abuse it. And ID resolution. That means at its core, its only job is to map one ID to another. That's it. Understanding this definition changes absolutely everything. To build this system the right way, we have to start with the one fundamental mathematical law that governs everything we're about to do. It's a constraint that we simply cannot escape. You know, the internet might feel infinite, but our pool of short URLs is anything but. The total number of possible short links we can ever create is just the size of our character set, our base, B, raised to the power of the key length, K. This creates an immediate hard upper limit on our whole system, and it introduces the very real risk of collision. So what does that finite space look like in the real world? Well, if we use a base 62 alphabet, that's all the numbers plus both upper and lowercase letters, and we pick a key length of 7 characters, we get about 3.5 trillion possible unique links. Now that sounds enormous, right? But for a global service that runs for years, that space can get crowded a lot faster than you think. And this brings us to the core tension of the entire system. Think about it. We need unique links that are also compact and easy to share. They have to resolve instantly, but they also have to be safe from attackers. The problem is, these goals are fundamentally at odds with each other. You just can't have it all without making some very smart trade-offs. Now we get to the single most important decision we're going to make: how to generate the unique ID. This one choice has massive consequences for security, for scalability, and for cost. So let's run the main strategies through the gauntlet and see how they hold up.
First up, the one that probably feels the most intuitive. Why not just take the long URL, run it through a hashing algorithm like SHA-256, and, I don't know, take the first 7 characters? The same input always gives the same output. Simple, right?
Wrong. This approach is a complete disaster in production. First, because of the birthday paradox, you'll get collisions way more often than you expect. It's also an attacker's dream. They can pre-compute hashes of common URLs to find your links. And you can't even properly handle things like URL variations or deletions. This strategy is just fundamentally broken. So our verdict here is clear. Deterministic hashing completely fails our most important requirements. It's not safe against adversaries, and it doesn't let us manage the URL lifecycle. It is a non-starter. Okay, so what about the classic database approach? Let's just use an auto-incrementing number for each new link. 1, 2, 3, and so on. Then we just encode that number into base 62. It's simple, and it 100% guarantees you'll never have a collision. But that predictability is a weapon for an attacker. Since the links are sequential, anyone can write a simple script to scrape your entire database just by counting up. This also creates huge database hotspots. Because all the new links are written in the same place, all that traffic hammers a single machine, which just kills performance at scale. So this is another dead end. The approach is basically an open invitation for scraping, and it creates performance bottlenecks that are incredibly expensive to fix once you have real traffic. It fails on security, and it fails on the basic economics of running the system. And that brings us to our winning strategy: generating a truly random, non-sequential ID for every single link. This immediately solves the enumeration problem. An attacker simply can't guess the next ID. It also spreads our writes perfectly and evenly across our database, which is exactly what you want for distributed systems. And here's the crucial architectural insight. We choose random IDs not because they perform best on an average day, but because they put a hard limit on the amount of damage an attacker can do. We are explicitly designing for the worst-case scenario, and that is the only way you can build a resilient, global-scale system. All right, we've picked our ID strategy. The hardest decision is behind us. Now we can actually start architecting the system. Let's build the blueprint piece by piece, always keeping our core principles in mind. Even a seemingly small detail like the HTTP redirect code you use is a critical architectural decision. A 301 permanent redirect tells browsers and CDNs to cache the result forever, which massively offloads traffic from our servers. A 302 temporary redirect, on the other hand, ensures every click hits our server. That's essential if you need to collect analytics or maybe revoke the link later. You see, this choice is a huge load-shifting decision, not just some minor protocol detail. So how do we build the read path for maximum performance? Well, we could start with a simple lookup, client to service to database. But that won't scale. So next, we add a cache, like Redis, to handle all the repeat requests. But to handle truly global viral traffic, we need to add a content delivery network, a CDN, at the very edge. The goal here is for over 95% of all clicks to never even reach our servers. And here it is, the whole picture. A user hits the CDN first. If it's a miss, the request goes to our redirect service, which then checks its own cache, and only as a last resort does it hit the main key value database. Every single layer here is designed to absorb the massive read amplification that comes from a popular link. Our design looks pretty good on a whiteboard, but now it's time for the real test. How does this architecture actually hold up when it's faced with the chaos of the real internet and dedicated attackers? This is where all our earlier decisions really pay off. A viral hotkey gets completely absorbed by the CDN. Those enumeration attacks we were worried about, blocked by our random IDs and some basic rate limiting. And for more complex problems like a cache stampede, where thousands of requests hit the database at once when a cache key expires, we use techniques like single flight locks to ensure only one request actually goes through to refresh the data. Every threat has a specific mitigation designed right in. So after this entire journey, starting from first principles, working through all the trade-offs, and landing on a resilient architecture, what is the single most powerful idea we should all walk away with? First, let's talk about the anti-pattern, what I call the staff engineer trap. It's that tempting shortcut. Let's just use sequential IDs from the database and put Redis in front of it. It feels easy, it feels fast, but it's a trap because it completely ignores the reality that your system will be accessed by adversaries. It prioritizes initial simplicity over long-term resilience. And that brings us right back to our real mental model. So what is a URL shortener? It's a read-amplified identifier resolution system where all the real costs, the infrastructure, the performance hits, the security vulnerabilities, are paid on the read path. If you design for that reality from day one, you'll build a system that can truly operate at internet scale.